Well, hopefully you can't hear the people talking through the walls in the room next to me, so I'll try a lecture here. If we're trying to describe a data set, we can do this by central tendency, we can do this by variability, probably better do it by both. But if we want to start with central tendency, most of the time the mean is going to be the most useful way to do this, and the reason is pretty simple. Of the different sorts of measures, mean, median, mode, the mean is the only one of the three that uses all of the data in your sample. In other words, when you calculate a mean, you add up all your values, you divide by the number of values. You use all of the data. The median on an odd number data set would only use the middle value. In other words, array your data from low to high. The middle value would be your median. It only uses that one piece of data. In the case of an even numbered sample, you'd take the two middle values in the ordered array and you'd find the average of the two. It still only uses two values. In the case of the modes, you may actually be dealing with extreme values. It's the value that's repeated the most often. Yes, we assume that's not the extreme of the data set, but theoretically it's possible. More problematic is that it only uses that value that is repeated the most often. Now, it's not that we'll dismiss the median or the mode out of hand. The median may be more useful to describe data than the mean in the case of some data sets, because the mean is influenced by outliers in a way that the median is not. If you have an extreme value in the data set, it's included in the calculation of the mean. It's not included in the calculation or determination of the median. So the median may actually describe the data better when there are extreme outliers, particularly in the case of small data sets. Now, the mode probably is most useful when you're dealing with qualitative data, and one of the sort of silly examples that I always cover in class is suppose we're interested in people's eye colors, and for the sake of argument assume we assign numerical values to those eye colors, as goofy as that sounds to you. A brown's a 1, a blue's a 2, a green's a 3, and so on. Well, my gosh, what useful information do we get if we calculate the average eye color? I mean, it sounds ridiculous on the face of it, but we might be interested in which eye color was most common. So you see that sometimes the mode actually provides more useful information than either the median or the mean can. Now, some of the same issues arise when we're looking at variability. The range can be useful, but the range is based on extreme values, the low and the high in the data set. So A doesn't use all of the data in the data set, it only uses those two values, and B is calculated by using the extremes. Well, I would tend to want to find variability by using all of my data, not just the highest and the lowest. That's why we tend to prefer the standard deviation and the variance. In a sense, they're like the mean, or in a sense they are a form of mean. They are an average measure of variability. Think about it. The formula requires you to sum values, right? Add up values like you do in the case of a mean. In this case, though, you add up square differences between the observations and the mean, and the formula requires you divide by the number of observations in a population, or one less than the number of observations in a sample. So it's much like calculating a mean. So we tend to prefer the standard deviation and the variance because they use all of the data. And this sort of average measure of variability seems sort of intuitively appealing in terms of describing data sets. But if I'm comparing data sets, actually I tend to start looking at the coefficient of variation, because what's nice about that is it takes variability relative to the mean. So I can see if one data set relative to its mean is more variable than another, and I have a number I can directly compare from data set to data set. I also point out you really want to look at the empirical rule, start thinking about this idea of what a distribution is, and also don't ever quite confuse the empirical rule with the normal curve. They're very similar, but they're not identical. Normal curves are very particular bell-shaped curves, not any old bell-shaped curve. I'd also point out, take a look at Chebyshev's theorem, because people are way too eager to assume that all data sets can be distributed normally or are distributed normally, and that the empirical rule or the normal curve can be applied to almost anything. It's not true. I'd also point out that take a hard look, and I did this in the written lecture too, at covariance and correlation. When we get to regression later in the course, those ideas are pretty fundamental to us. I mean, we want to know how variables relate to each other. At this stage of the course, we're not really spending much time on that, but later in the course, we'd want to know if some variable x was correlated, moved closely with some other variable y. Particularly because we might want to predict variable y, and we might find out that x is very helpful in predicting it. Covariance, again, the idea that variables vary together. Those things are very useful to us when we're building models later in the course in regression to try to predict variables. And I think it's a good time actually to get a start on that, because you do have a case that's due and you need to start thinking about this idea of building models and variables moving together.